Start. Okay. So, day 26. Today we're talking about galaxy clusters. Um, so we've got two numerical assignments to go through and two readings, and I'll go through those pretty quick. Not a ton of questions on these readings, but that's okay. It's more straightforward than some of the other stuff that we've covered before. There's no weird expansion or stuff. It's just kind of applications of the same ideas that we've been looking at. We'll start talking about galaxy clusters. Okay, let's go through the questions real quick. That is completely illegible for being so small. Let's see if we can make it even smaller. All right. Okay, so the Max BCG catalog. One of you was unclear about what that actually is about. So I'll maybe say a little bit more about this, but the basic idea is you have a picture of the sky that just looks like a bunch of stuff. And that stuff is distributed from close to us to really, really far away from us in this huge range of redshifts. Redshifts here being distances away from us. So the question is, I got all these points of light. Most of them are galaxies. There's stars in our galaxy that we can see that are in the way, but basically anything outside of the galaxy is a galaxy. How do I know which ones of these are clustered together? How do I know which ones of these know about each other? How do I know which ones of these make an actual object and not just things that happen to be passing close to each other? So constellations are not real objects. A constellation in the sky, Orion or Virgo or Cancer or whatever you have, whatever your sign happens to be, that's not a real object. They just happen to be lined up that way, and it makes us feel something. They have no influence because it's not a real object. It's just a chance alignment of stars in the sky. Right? I want to figure out what of these things are real objects. So what Abel did was he said, well, we'll look at the biggest thing and then the next biggest thing, and then let's look at just the biggest thing. So the biggest thing might be just another object that's really close to us. So if one object is really close, but it's not actually related to everything else, it's going to look way brighter. So let's not look at that one. Let's look at a couple down. And so Abel came up with these optical things where he just looked at a picture of galaxies. So he was doing this back in the 30s, I think, 40s, and he just had these images that are just plates of glass with little dark spots on them. So he needed to do that to figure out where these objects are. He didn't have much to go on, but I can learn about where these things are in space too, in 3 dimensions, right? So there's a third dimension that we can start to consider. So how do we get at that third dimension? Well, I need to know the distance to every one of these clusters. That's a headache. Distances are hard, right? So we'll use the redshift because that gives us a proxy for the distance, or we can use the color, which gives us a proxy for the redshift. So we'll go through all of these stunts, and I'll talk more about this in a little bit. We go through all these stunts to try to filter out which of these objects are actually related to each other in space. So the Max BCG looks for really bright objects. So it looks for the biggest objects in the cluster, which are often a couple times bigger than anything else. And it looks for this red sequence, which I'll talk about in a minute. So the red sequence is extremely useful, and we'll talk about it in a minute. So that catalog is like, well, we're just going to take all of these things that we see, and we're going to try to make a cut on this big data set to cut out all the things that aren't in our galaxy. And they have some criteria that I don't actually remember, and I didn't get a chance to go through the text in careful detail, but I will next time. There are ways to define galaxies, and then there are ways to find them. And the Max BCG looks for really bright galaxies and then does redshift cuts around that bright galaxy. So it makes color cuts to cut out things that are redshifted either too far away or too close if the redshifts don't match up. What does diverging mass mean? So this is an important question. When we're talking about that thunder or is that somebody rolling a toter?
Sounds like something rolling.
Somebody rolling. I thought it was thunder for a second. I was like, boy, that storm just keeps going. Where the hell was I? Oh, diverging mass. Okay, so I have some density, rho of r. The total mass within some radius r is the integral from 0 to capital R of rho of r d cubed volume, where this is over the radius. Probably need 2 other integrals in there too, because I have 3 integrals to do, right? So if my mass goes like 1 over r squared, the volume integral, what's this if I'm in spherical coordinates? What's the volume element? Right. R squared sine theta dr d phi d theta. I can do this integral, and this just gives me a 4 pi. So I just get r squared. So this integral turns into the integral from 0 to r of 1 over r squared times 4 pi r squared dr, and I've done the other 2 integrals. This cancels with this, and I'm just left with 0 to r of 4 pi comes out, dr, which is just 4 pi r. I hand waved past a couple of things, and I got the only thing that I wanted, which was the r. So when I do this integral, the 1 over r squared cancels the r squared from the mass, or from the volume. So the density goes down, but the volume goes up, and they both cancel each other out. So if I start integrating, and I keep going out, the mass just goes up and up and up and up and up and up. There isn't an end to this thing. If I take the sun, and I pull this same stunt, what's the sun's mass do? The sun's density is large until the surface, and then it's basically 0. So if I do this same stunt, I'll have something that looks like a step function. So as I increase my density, it falls off like a rock at the solar radius. So I can keep this integral going, and I don't get any more mass, because all the mass stops here. That makes sense? But with a 1 over r squared, in principle, that mass will continue going out and be a problem. So this is problematic when you want to define the edge of a thing that is self-gravitating. And then I get into my research stuff that you don't want to hear about, or maybe you do, but I don't want to get into it because it's messy. So this 1 over r squared thing, if you went to my talk back in February, I had this one spot where I have all these stars forming, and they all form really powerful 1 over r squared spheres. If you look at the density versus radius, it looks like 1 over r squared for most of the range of the thing. And what this diverging mass means is that can't be the whole story, because otherwise it would be infinitely massive and infinitely large. So there's got to be more of an edge to these things, but we don't understand that yet. But the gravity makes things go like 1 over r squared. So we're going to go with 1 over r squared and then just kind of draw a line at the edge, typically. Abel's criteria was solid angle. So his criteria says that the distance between each cluster and I think the third brightest cluster member is something like 1.7 arc minutes over the redshift. So this over the redshift, so as the redshift goes up, this angle criteria goes down, right? Because as here's me, here's a cluster at 1 redshift, here's the same size cluster at another redshift. That's a smaller angle by however much further away it is. Does that make sense? So the angle goes like 1 over z so that it takes into account the distance. So I need this guy to be here, but if I take this same thing and I use the same distance, that's a much bigger angle because it's closer to us. So the angle thing has to depend on redshift, and it just goes down with redshift. And it's kind of coarse. I don't know why 1.7. 1.7 came from, he had looked at a whole bunch of galaxy clusters and said, well, that's about how big they are. What is dynamical friction? I will go through dynamical friction in the end, but this is a lot like if you're ever in like moderately heavy traffic, which you never see moderately heavy traffic here. It's either at a standstill on Thomasville or there's no traffic at all. But if you're going down like a major highway, and you see a big semi truck that's going slower than everybody else, there's always a tricky spot right behind that semi where cars will collect and get stuck because it's hard to get out because the traffic's going fast on the sides. So things will kind of focus behind the semi truck. This is a terrible analogy, but this is what's going on. So you get something massive and it's traveling, it drags all the stuff behind it. I'll draw better pictures in a second. What's the difference between Abel's catalog and the modern optical catalog? So the modern optical catalogs get to use color, and they get to use redshift information in ways that are more sophisticated than what Abel was able to use, because Abel had a plate of glass with little black dots on it, and we have computer knowledge and color knowledge. So the modern optical catalogs have a lot more information and are a lot more thoughtful. What mass to light ratio would not need dark matter? So this is a good question. This isn't exactly how you phrased it, but this is the basic idea of what you were going after. So let's talk about mass to light for a second, because we talk about mass to light ratios of several hundred now. So upsilon is the wine glass Greek character. This is the mass to light ratio in units of solar. So it's really like that, right? And I'm going to pull up these scaling relationships because I'm going to say something wrong if I don't pull up the right answer. It's in here, right? There it is. Okay. Luminosity. The reason I pull this up is that way I know where to find it, to be honest. But this way you know where to find it too. So the scaling laws are in the second lecture notes. So the luminosity, this is the only thing that we need, is what the luminosity does. So the luminosity goes like the solar luminosity times the mass in solar units to some power alpha. And alpha goes like 5 for low mass stars, and like 4 for higher mass stars. So what's the mass to light ratio? So luminosity goes like solar luminosity, m over m sun to the alpha. So what's the mass to light ratio? Mass to light is going to be mass over this nonsense, m to the alpha. So this is just going to be m to the 1 minus alpha, right? So when the mass is less than 1, let's say the mass is a half, then alpha equals 5 for the mass less than the solar mass, and 4 for mass is greater than the solar mass. The number doesn't really matter too much. What matters is that the mass to light ratio is going to go like mass to the 4th power, right? So as it gets less than 1, that number goes down. So the mass to light ratio is less than 1 for things less than the sun, because this is a negative power. And it's a little bigger than 1 for things bigger than the sun. But how big can it get? If I have a 10 solar mass star, the mass to light ratio is going to be enormous. But how many of those do we have? So if you wanted to sort out what the actual mass to light ratio is for a galaxy, and I realized this as I was doing this would be an awesome homework. The integral of m low to m high of, we want the average upsilon, so that's going to be the total mass times the salpeter function, the mass distribution, divided by the total total luminosity, which is going to go like n to the alpha times, again, dn dm. So this dn dm kills all the massive things, right? Because you know this, the number of massive stars falls off like crazy. So what should this light function look like? I should actually plot this, and I may make this a homework function, or a homework problem, because the more I think about it, the more I like it as a function, because it gets your head around what values epsilon can take. It's going to be like 1. So let's back all the way up to the top. I'm going to cut to the short answer, and then I'll tell you the actual long answer. What mass to light ratio would not need dark matter? Something that's like 1. Because the sun has a mass to light ratio of 1. And if I had 10 to the 12 suns, what would the mass to light ratio be? 1. Because the mass is 10 to the 12, and the light is also going to be 10 to the 12. Right? We're just going to add them all up, right? So if I have a buttload of solar mass stars, the mass to light ratio is 1. So if I integrate that out, we can get some parameters for what ranges of mass to light ratio are expected, but we typically expect them to be about 1. 300 means that the entire galaxy is made out of O stars, and you can tell that it's not because you'd be able to see that. So mass to light ratios of like 1 are what we really want to see. How do tidal forces pull stars from other galaxies? Let's talk about the tidal. I'm actually going to leave this up. I gotta write this homework problem. If I have my ducks in a row, it'll get assigned, but my ducks get out of rows like it's their job. Tidal forces. So here is an object. I don't care what it is. It's a star. It's a duck. Ducks are not likely to have a strong accretion. Let's call it a star for now. But this will work if it's a galaxy too. Same story. Here's a star. Here's another star. Maybe it's the same size. Maybe it's a lot smaller. We'll pretend it's a lot smaller for now. If I've got, so I know that for this, the force that a thing experiences gm n over r minus r1 squared minus. So that's the force from 1. The force from 2, let's call this guy 2, is going to be similar, gm2, little m is me, over r minus r2 squared. Oh, that's 1. That's 1. I was going to go for the homework first and then go through the reading, because that makes more sense. Don't let me start the lecture notes without going through the homework. So the force from 2 is going to be like this, different mass, different radius, but we've got this balance of forces. And the force that I'm going to feel, this is me in my space helmet. I'm between these two guys. It's going to be the sum of these two forces, right? So which direction am I going to go? Am I going to go towards this one or this one? Well, it depends on which direction the force actually is, the net force. So if we draw a surface where F1 of R plus F2 of R equals 0, okay, I'm actually going to sneak in here. I'm going to sneak in some Coriolis force here too, because I can't have two stars next to each other unless they're either running into each other or in orbit around each other. So let's pretend that these two stars are in orbit around each other for now. So if I look at the space where the force from this plus the force from this plus the Coriolis force from everything rotating, and I have to add that in, otherwise this picture doesn't make any sense, you get a thing that looks like this. So this is the equipotential surface where the force and the Coriolis force cancel all the way out, and things don't matter, and you can't feel anything. Does that make sense? So this equipotential surface has 5 points that are stable. No. Where everything cancels out completely. They're called the Lagrange points. You heard about these? No?
All I know is that James Webb is at the Lagrange point.
That's right.
One.
Which one?
Is it 2?
It's L2. Where is L2?
So between the sun and
It's not. So that's
I feel
L1.
like it's like further
Between
out
the-
than us.
the
That's
moon,
right.
The moon and the Earth, right?
No. It's further out than that even. It's like, so the moon is about 250,000 miles from us. L2, so the sun is here. The Earth is here. L2 is out here. It's on this spot here. Because of the Coriolis force. So I mean, here you just see all that gravity, right? But the Coriolis force is what does the balancing. So L2 is out here. L1 is in the middle. L3 and L4 are here and here. Am I missing one? I'm sorry, my brain is totally farting. Is there a 5th Lagrange point? Anyway, these are the important ones. So lots of satellites get stuck here in the Sun-Earth system. The things that you want to point at the sun, we put here. This is like 1,000,000 miles in, and this one is like 1,000,000 miles out for the sun. The moon is only 250,000 miles, so the moon is well inside the Lagrange points. So what happens is as the Earth goes around the sun, the Lagrange point just follows, which is why we put the telescope there, because the telescope, A, is further away from the sun, B, it's further away from the Earth. The Earth is hot and radiating in the infrared, so we want to get the telescope far away from that. Also, it's doesn't have the Earth ever getting in its way. The Earth is never in James Webb's way, whereas if it was in orbit around the Earth would be in the way. And if it was here, the sun is in the way, and the telescope really needs to be cold. So we put it out here. So these are called, so this thing that I drew is called the Roche lobe, and it's the point where inside this lobe, stuff is attracted to this guy. Inside this lobe, stuff is attracted to this guy. But the attraction gets lower as you get towards the edge of the lobe. So this is something that's interesting, and I think it's actually very important because we see a lot of dust and crazy stuff that gets kicked out of binary stars, but not from single stars. Because this now has a 0 in the potential. If I just have one star, how big is the potential? How big is the lobe of things that are attracted to it? If I have one star all by itself in infinity, like it can go out to infinity, the tidal effects of this force of this star fell way out here. So the 0 of the potential is really far away if you just have one star. But if I have 2 stars, there's a 0 of the potential between them. So I can have something kind of shoot over here. If there wasn't a star here, it would just rebound. But it could go here. Now it's not bound to anybody, so now it can leave. Or get bound to this guy, but sometimes they leave. So when I have 2 objects next to each other, the tidal force is the force that you experience from outside objects. It's the force that you experience because you're not a point. So here you are a planet or whatever. So an object experiences tidal forces from outside things because it's not a point source, because there's structure to whatever galaxy. So a galaxy has some structure. Something else comes by, and it's going to rip off some of these low-lying stars. And because they got ripped off doesn't necessarily mean that the other galaxy gets to keep them. Sometimes they fly out into the intercluster medium. So, does that make sense? More can be done with this, and it's interesting stuff. But
How far out would you say like L2 and L3 and L4 are?
from the Earth, for the Earth Sun.
Yeah, like you know how you say L1 is in between the Earth and the Sun?
Uh-huh.
So what's like... So L1, is that like a half AU, or is it just like any...
It's the balance, so you got to balance the 2 forces. The force from the sun is going to be bigger. So it's closer to the Earth than halfway.
Okay.
That makes sense. I don't know exactly how far off. You can look it up. It's like 1,000,000 miles though, so it's pretty far.
That sounds about right.
Um, yeah, might be 1,000,000 kilometers. So it's a million somethings. That's a true statement, regardless how far away it is. Yeah, so there's all kinds of cool things. So it's funny because L1 is the only one that's a stable orbit. L2 is not a stable orbit because as soon as you go over here, then you're not there anymore. So you have to orbit this spot, which is why they talk about James Webb needing propellant. So there was a big announcement right after it went up, right after it actually got to L2. They were like, hey, we can run it for probably 40 or 50 years, not the 10 years that we originally budgeted for because we got there without using up too much juice. So they need that little bit of extra gas to stay in orbit. It needs a push every time it gets to the side. A little bit of nudge, but not a lot. So tidal dynamics, tidal forces are super interesting. Was that
So it doesn't go around
the James Webb? No,
it just keeps going.
it's in orbit around the sun, which is an intriguing thing. It's no longer in orbit around the Earth anymore. They boost it to an orbit around a much bigger object. And then later, when it's done, they'll kick it into a trailing orbit. So they'll just kick it this way a little bit. So it will slowly get further away once all its propellant is done and we can't use it anymore. Unless we figure out how to get a person there, which would be pretty neat if we could service it. But
Maybe it could be like Voyager, just like keep on going out.
yeah, well, that would take a lot of energy because it's actually really hard to get to interstellar space. It's harder to get to the sun, but it's really hard to get to interstellar space. And what are projection effects? So this is an innocuous question, but heavy, because projection effects are really a huge amount of what underpins why astronomy is a headache, and the headaches in astronomy. And the upshot is, all of these objects that we deal with are three-dimensional and basically round. I mean, more or less, they're round in one axis or another. So if I want to get, for instance, the volume density in grams per cubic centimeter, I can't do that because what I get is the integral along the line of sight from 0 to infinity of my density. This is called the column density. It's not a function of the three-dimensional position, it's a function of the two-dimensional position on the sky. We'll call that n hat for a second. So projection effects do things like integrating out degrees of freedom that you actually want. Like I need to know where things are in Z, but I don't have it because it got integrated out. We can get it back a little bit, but sometimes it's really impossible. So if I have a thing that's the size of a galaxy cluster, it's really hard to tell the back side of the galaxy cluster from the front side of the galaxy cluster because they're small compared to their distance. I mean, they're big, but they're also very far away. So one of the things that it means is you can see two things that look like they're next to each other in projection. So if I'm sitting on the ground looking up, these two things look like they're related to each other, but they're not. So projection effects are basically the integral that you have to do when you're looking at things outside of our galaxy. Let's see. This is all stuff that I'm not going to get to until later, but I'll go through them because I have them up. What is quasi-steady state? So steady state means that the time derivative actually goes to 0, and that thing will stay put forever. Quasi-steady state means that the time derivative is small, but not 0, so it'll stick around, but not forever. So this is important when we have these cooling flows. So we talk about these king spheres or whatever, and the issue is that the cooling rate goes up with the density. So, and I'll talk about this when we get to X-rays. So as the density goes up, the cooling rate goes up, which means that the temperature goes down. But I needed that temperature to keep the whole thing supported. So when the temperature goes away, then it's not a 1 over r squared anymore, and it'll start to contract. Or maybe it'll collapse. Maybe something else will happen. So that's what quasi-steady state is it's kind of steady state, but there's something in there that you missed. Y parameter I will do because I need to do math for that. Why do cooling flows become inefficient in low T? Because the cooling rate is proportional to the temperature. When we'll get to Bremsstrahlung, I'll show you that. In these mass scaling laws, does the mass include the dark matter? Yes, this is important. It's the dynamical mass, not the luminous mass. So there's two masses that you need to think about. There's the dynamical mass, which includes the dark matter, and the luminous mass, which doesn't. Why is near infrared less dependent on star formation history? Sorry, I'm not stalling because I don't know. I'm stalling because I'm not sure the best way to answer the question quickly. And maybe I want to turn it into a question where I ask you. This is a great question because it underpins how that whole single stellar population business. So if you remember from the single stellar population, the left side of the graph is where all the O stars peak, and that drops steadily fast. But the right side doesn't really evolve very much. And if we could keep that going out to the near infrared, that doesn't evolve much at all either. So the near infrared is mostly caused by the thermal component, which you can see through the dust of low mass stars, which stick around. The near infrared part isn't nearly as destroyed by all of the O stars dying. So when all the O stars die, the near infrared doesn't really care. You still see all the same AFG stars that you would see before. What is Sunyaev-Tseldovich? The short answer is CMB photons that get heated up by X-rays. The quantum mechanical correction factor, I actually don't know, and I didn't look it up, so I'll have to get back to that. And why does SZ happen? Because I got a photon and a hot electron. That hot electron smacks that photon and kicks it up to a hotter photon, and it cools off the electron. But I can't see the electron, so I don't care. But it heats up the CMB photon. I'll talk in depth about that. And what is the beta model and the beta discrepancy? So the beta model is treating things like singular isothermal spheres, which is dodgy, and the discrepancy is that dodginess showing up. Also, dark matter. I'll talk about that in more detail later when I do math too. Okay, I'm going to go through. Does anybody have any questions on the questions? Yeah.
Why do they always like restate like, oh, this is the missing mass and this is the dark matter mass? And, like, why do they always have to do that like every quarter?
Because it's still novel for us.
Once would have been like enough.
Well, you see it. You see it in different ways in different places. So, like, you see it in galaxy clusters because they're not spinning fast enough. You see it in you see it in individual galaxies because they're not spinning fast enough, and that's one piece of physics. But if we see it in a cluster of galaxies that have way too much X-ray, that's a totally different piece of physics. Maybe it's different completely. Maybe it's all the same answer. So, but that's why, because every time we go to say what's the mass of that thing, it comes up wrong. Or kind of regardless how we do it. Okay. Homework. Let's do 5 and 6. We'll go off last year's. Okay, so the color of the sun. So color, B minus V, is minus 2.5 times the log of the ratio of the luminosities plus C. The ratio of the luminosity in the B band to the ratio to the luminosity in the C band, and the color, and the C is a thing we gotta look up. We'll just look that up. So the first thing we want to think about is what's a filter mean, and the reason that I have this homework set is because I wanted you to start putting your heads on what a filter is doing to a spectrum. All it's really doing is you're taking your spectrum and you've got your filter, which is wavelength dependent. You multiply them together and you integrate, like zipping up a zipper. And the total luminosity is just going to be your spectrum times the filter integrated. That gives you the luminosity in that window. So if my filter is a delta function, then I just get the frequency at one wavelength, or that I get the flux at one wavelength. We typically are going to call our filters Gaussians because a delta function lets through all of the photons that are exactly at one wavelength, so it has zero actual transmission because it's only letting through one photon, and no photons have that wavelength, so they all got redshifted one with the other. So you need a photon. Your filter needs to have some width. You have to be able to accept a range of photon energies. So we treat them like a Gaussian. A Gaussian is some normalization times 1 minus lambda minus the central density over the width of the thing. So here's a Gaussian, which has a center and width. So the full width at half maximum is easier to eyeball from a plot than the variance is, because the variance shows up if I've got a Gaussian. The variance shows up at 2 root 2 above below the maximum, but the full width half maximum is just half, so it's much easier to eyeball. You just go down by half. That's the width, and they're related to each other in a Gaussian. Like this, it's the square. It's 2 square root of 2 log 2, which is a really funny combination of things involving 2. It's the 2iest thing you can make. So the sigma is just the full width half max divided by this number. It's like 1.7. So then we define our Gaussian as e to the wavelength minus the center squared divided by 2 times the width squared. Yeah.
So I wasn't able to find the solutions to this on Canvas. Where on Canvas is it?
Is which?
The solutions to homework 5. I see that there's solutions to the paper homework, but
I haven't put them up yet.
Oh, okay.
Yeah, I'll put them up now that everybody has them. I'll put them up.
All right.
So our Gaussian is just L, our wavelengths, minus the center, which we pass in, minus the width, which we also pass in, or whatever. And then, okay, here's this other mystery bit. The normalization is the width times the Gaussian, and I just add this up. I do this because I need the filter to add up to 1 by itself. So if I just integrate everything on the filter, I have to get 1. Otherwise, I'm going to be injecting information into the signal that I get. I'm not just going to be extracting that part. I'm going to be extracting that part times whatever the normalization of my filter is. Does that make sense? So that's what we're doing here. Now you could do this with, I know that a Gaussian is normalized by 1 over 2 pi sigma squared, square root of that. This is the normalization for a Gaussian. But I don't have a Gaussian, I've got this numerical thing, which is a little different. This is a good approximation, but you actually need to get the finite size of the bins in there. So it's way easier to just say, I'm just going to normalize it. So we'll add up whatever it is and divide by that. So I know that it's 1. It's exactly 1. So then my filter is going to be centered at this center and have this width. So that's what this looks like. So if we plot a filter with its full width half maximum indicated, we got that there. So if you everything that you need for this homework assignment is actually in this block. So if we plot a black body, that's just, you get some luminosity and some temperature. T sun is 5700 Kelvin, so we'll use that. So we want the B filter, which has a a central frequency of 445 nanometers and a width of 94 nanometers. And the V filter, which has 550 and a width of 87. So we'll make the filter for the B, and then we'll get the luminosity for B. I don't actually use it in this block. This is what I want you to do in the next block, but I did it here. Then we get the filter for V is again just a Gaussian with those two with the wavelength and center, and then we can plot them. So I do this axis thing because they have different scales. So the filter goes from 0 to 1, and the black body goes from 0 to 10 to the 14. So I plot them on different scales. So one is plotted on the right, the other is plotted on the left. And here's the V filter, and here's the B filter. So this is my black body, and these are my two filters. So we just suck out how much we want of those. This is the bit that you need. So color is then the ratio of the logs plus this number, and this number I just give you, it's up there. It's the log of an A star minus the magnitude of an A star, which is like 0, but it's not actually 0 because history. So, okay, so the first thing was plot a black body, which is just that. The second was plot my colors. So this is my V filtered spectrum, and this is my B filtered spectrum, and you can see that the filters are picking up the signal where it's supposed to be on the black body curve. And then you take the ratio and you get 0.526, which is a little bit bluer than 0.63. But this is the answer that you ought to get. The difference between this and what we actually see is the stuff that's in the way. So the black body is making a black body at the surface of the sun, but then those photons have to all travel through the atmosphere, and that makes it a little redder. Yeah.
When Python gives an error about the log, is it because I didn't put the base on it?
No, it depends on. Yeah, if
Oh,
there isn't a log by itself, you have to take log from NP. Now, NP is where all the math functions are.
okay.
Okay. Any other questions? Any questions on this one? Are we all right? Nope. Okay. So the upshot of this is what I wanted you to be putting your hands on is how does a filter work? How do I get a color from a spectrum? So I need two filters. Filters are these little pocket functions that just suck out parts of things, and then you take the ratio and you get there. Okay, so this one, we do the same thing. So here we have all the same stuff that we had before. So the first thing I asked you to do was plot B minus V versus the temperature, which is straightforward. You just do a scatter plot of the star data B minus V versus star data T effective. What's wrong with this plot?
You got them flipped.
My axis label's flipped.
It looks similar.
Yeah, that's because I was being a space cadet. Right. The first thing is X, so that's got to go with the X. So you should get that. Next, I wanted you to write a function that takes a temperature and gives you a color, doing exactly what we did in the last thing. So make a black body, make two filters, get the color from the filters, spit it out. Now you can actually do this analytically by just integrating over the black body function, which is a fun thing to do for some value of fun. And then get B minus V for the sun here, which you should get the same thing you got in the last homework. And then I want you to loop over temperatures and plot the black body and the star data on the same plot. So what this is doing, so you can see that the stars, the black body is in red and the star is in blue. The stars are all in blue. So you can see that a black body is a pretty good approximation to the color of main sequence stars. So we call a main sequence star a black body. That's pretty good. There's slight differences. The slight differences come from the atmosphere. You can see they go away largely. They're really most prominent at these kind of lower temperatures. Lower temperatures, that's 10,000 Kelvin. That's pretty hot. But lower temperatures, you get a slightly redder envelope star than what you get from the black body because of the atmosphere of the sun, or the star. And yeah, I appreciate everybody's feedback on the last one too. That was very useful. I will. So some of you said they were too easy, and some of you said they were too hard. And I feel like I must have gotten the right balance because I feel like I got it. So in the future, I'm going to try to add a little bit more support at the beginning, but I can't add too much because the grind of not knowing how to find the thing and sorting it out is a big part of it. Like, how do you program? Well, you got to go figure out how to find the information that you don't know, and that's part of it. So how to introduce the grind without making it really unpleasant is a tricky thing about being an educator. But I do appreciate everybody's feedback. I'll do what I can to make that stronger. That's not what I want. I don't want either of these. I want this one. Okay. That's the homework. Now I got 20 minutes. Cool. Clusters. So clusters are cool because they're the biggest objects in the universe. And being the biggest objects in the universe, oh man, I made edits to a version of the document that isn't this one. I edited the one in last year's. Anyway, okay, clusters are large. So these are the largest objects in the universe. So okay, this here I specified gravitationally bound, because I mean that's what object means once you get large enough. If it's the only thing that really makes an object is if it feels its own gravity. So some objects just look like objects. So like you can find lines of quasars in a line. That doesn't mean that they're real because they're separated by millions of light years in the z direction. These are gravitationally bound. Most importantly, they're actually, we call them galaxy clusters, but they're not galaxy clusters. They're dark matter balls that happen to have galaxies in them, because that's what's going to happen when you get a whole bunch of crap. Galaxies form. So they're large, and they're largely dynamically relaxed, which means that they're pretty stable. We know that these aren't objects that are like exploding or forming. So they trace the dominant density fluctuations in the early universe. And they have a lot of galaxies, so they're good for studying really massive galaxies. This is where you find all these CD type galaxies. And it's really useful to learn about mergers of galaxies and galaxy-galaxy interaction, because that's where all the galaxies are hanging around a party. And we have these extraordinary environments. So the temperature is like 10 to the 7 Kelvin. That's really hot. And this is like high vacuum. The density is like 0.1 particles per cubic centimeter.
So this is like between the galaxies and like between them in the cluster.
Yeah, it's the intercluster gas. So the galaxy is just a galaxy. It basically behaves like a galaxy. So here's my cluster, and I have these galaxies in it, but then I have all of this hydrogen that's in here as well. And it has a density of like 0.1 particles per cubic centimeter. The density of the ISM in the galaxy is like 10. So this is 100 times less dense than the outer space that's near us. Outer space doesn't have much stuff in it unless you have a whole lot of outer space, and then there's a whole lot of stuff. So this is 0.1. This is well above or well below any vacuum we could ever possibly achieve on Earth. So the closest that we can get is about 1 million particles per cubic centimeter. It's really a pretty high vacuum. This is really small. So this is really outer space, but I have 1 million light years of this stuff. So there's actually a lot of stuff here. And it actually is really hot. Because of that mass, because visualization, okay, V squared equal GM over R. V squared is KT too, right? That's a dodgy assignment. It's all right. It's the energy. So KT is the thermal energy. 1/2 mv squared is the kinetic energy. So we'll just think about this side. So m is so large that t has to be huge to accommodate. We'll talk about X-rays in a minute. Uh-oh. The video went away. That's too bad. That's annoying as hell. Now you show up again. Sorry. This is just for the people at home. Oh, there it is. That was weird and annoying, and I apologize. Here I am. That's what I'm talking about. Okay. Okay, groups versus clusters. So, relatively arbitrary, because I could have 2 galaxies that are bound to each other. I could have 3 galaxies, or 4, or 5, or 6, or 7, or 8, or 9, or 10, or 11, all the way. I can just do that until I have tens of thousands of galaxies. There's nothing that requires 5 galaxies to be together. I can just have 5 galaxies together. So at some point in time, it's a cluster, and it's a big ball of dark matter with X-rays in it, and at some point it's not. So I don't do clusters, so I'm not really great at, yeah.
Was it hard to define like where the cluster ends?
If you're using the X-rays, no. If you're just using the galaxies, yes. So we'll talk about that in a second. I'll show you an X-ray picture, and you can see it. You can see the X-rays stop. A supercluster is a bunch of clusters. So I'll show you one of those. It's not in the book, actually, because it's been discovered since the publication of the book. So we live in this local group, and the local group is the Milky Way and Andromeda. M31 is the other, M33 is the other spiral. It's not very big, but it's another spiral galaxy. We also have the Large and the Small Magellanic Clouds and a bunch of little dwarf things. So that's what all these guys are here. So we have, let's see, we have M33 and M31. M31 is Andromeda, and M33 is a spiral that's orbiting M31. We have us, the Milky Way, and then all of these little dudes, the SMC and the LMC, which are some of our favorite galaxies because they're pretty big and pretty close to us. Also, they both have low metallicity, which is cool because it gives us a different environment to look at. Okay, so there's 2 weird things. There aren't enough dwarf galaxies. When we go look at this and count up all the dwarf galaxies, we come up short by a factor of like 8 or 10. So that's, yeah.
You mean in the local group?
Yeah, in the local group. So that's a good question. So the count of dwarf spheroidals are really only about the local group, because we really can't see them around other galaxies. That's the problem with dwarf spheroidals and dwarf galaxies. They're really little, so they're really hard to see, and the galaxy's in the way for a lot of them. So there's not enough dwarf galaxies, and people will use this as a dig against this lambda CDM that we spent all our cosmology time talking about. I think it's observational. I think it's bearing out to be observational. People keep finding these other little tiny galaxies. One thing that isn't observational is all the galaxies do seem to be in a plane around the Milky Way. So the Milky Way is like a frisbee, and all the galaxies are orbiting like this, like a plane that cuts it down the middle. That's weird. Yeah, it's got to come from the formation. And galaxies tend to form in filamentary stripes, or intersections of filaments. So you will have a tendency to have things lined up along with the filaments. So that might be a real thing, but I don't really know. So that's curious. Yeah.
Because in the book, like, oh, we have this much here, and then a little further away, it's like even smaller and smaller, and then it's like very far away, it's a big thing. So it's like our immediate area, there's like not much. Is it like, or am I like thinking the wrong way? It didn't seem like there was much in like like even within a couple megaparsecs of us?
So this edge here is a megaparsec, and that encompasses all of these little dwarf galaxies and all of these dwarf galaxies. So you can see dwarfs around Andromeda too, as our buddy. And then there's some stuff over here. So here's what the kind of super picture looks like. And we're here, and this is the local group is this little black dot. And then there's some more stuff, and then some more stuff. It's not like constantly dense like a city. It's like pockets, more like Europe, where there are pockets of very dense cities. Does that answer your question?
Yes. I'm not exactly sure how to phrase it as well. Because like I feel like a while back I saw this video where it's like, oh, there's like large pockets of space, but it's just like no galaxies. It's not always constant. And we're like, the way they describe it, I don't know how like actual factual it is, but they're like, okay, so we're like in this little bit that's inside of like a big expanse of not much else. And then outside that there's like clusters and like super clusters, but we're just kind of in the middle of.
I can't address that video because I haven't seen it, but I can show you this, which is a picture of everything that's nearby. And so by looking at where the stuff is going, by looking at the velocity vectors of all of the galaxies, we can make a map of what the gravity is doing. Because velocity and gravity are related. It's a little bit more complicated than v squared equals gm over r, but not any more complicated than the last time I showed you gravity, grad phi. So there's stuff. I mean, it's outer space, so you can draw a region that has absolutely nothing in it. But there's plenty of stuff, and it's not like I don't think that our cluster is any place particularly special. I don't think. But the world is a complicated space. Okay, I'm going to do this local group mass, and I think that's what I'm going to run out of time for. And one of the things that I find is short about this is he doesn't go into the luminous mass as much. Excuse me. Because that's not as easy to do by hand. The luminous mass is, okay, you take a picture and then you run it through a couple of numerical integrals and then you get the luminous mass. So it's not as interesting, but the dynamics is relatively interesting. So let's just try to get a mass of the local group by looking at what Andromeda and the Milky Way are doing together. And this is going to give us a mass that's 20 times larger than the combined mass of Andromeda and the Milky Way. So the basic idea is we assume that, so we have Andromeda and we have the Milky Way, and at the beginning of the universe they were close together but moving far apart with some velocity. So we'll keep the Milky Way fixed and we'll draw Andromeda. So time goes in this direction. Andromeda is going to go out that way and then back in, and Milky Way will stay put. Right? So they fall away. So this is just like throwing something up in the air and trying to measure the mass of the Earth. So the Andromeda is like here. And there's a place here where they are the furthest away. So I know that this time is basically the age of the universe. And I know, so this is where Andromeda is, and I know this time is basically the distance to Andromeda, which I know, divided by the velocity that Andromeda is going to smash into us with, which I also know. So this is now, this is the future. So what we want to do is get what this is, which is going to get us what the mass is. How does it get us what the mass is? I'll show you. Okay, so 1/2 v squared equals gm over r, almost, plus a constant. A constant sets the zero of the energy. That's important. You always got to set zero somewhere. And because of gravity, because it's the potential energy, you can arbitrarily do that. So we're going to just say that this is equal to gm times 1 over r from this guy minus 1 over r max. So my constant is just this. I want to do that because that way at r max, v equals 0. That's a great way for me to set my boundary condition up. This is where the velocity is 0. And we can see this m is what I'm looking for. V, I can measure. R, I can measure. So let's go ahead and do that. So this is dr dt. So dr equals this business here, 2 square root of 2 gm times 1 over r minus 1 over r max, square root of this, oops, no, yeah, okay, this is dr dt equals the square root of blah, so this only has r in it, so all the square root of blah goes over here and the t goes over there, so I'm left with dt equals 1 over the square root of this thing times dr. So then what I want is just, I want an indicator of, I want this point here, so we'll just integrate from 0 to t max of dt, which just gives us t max, equals, we'll do this integral, and he did it for us. It's just a u substitution, it's straightforward. You get pi times r max to the 3/2 over 2 root 2 gm. Right? Now I also know that t max is equal to half the distance, half of this distance, so 2t max equals the Hubble constant plus b over v, which I measure. So we'll get this 2 over here, over 2, over 2. And I can assign these two things to be equal to each other. And then do a little bit of algebra. T naught I know, v I can measure, v I can measure, that's just the redshift. Andromeda is one of the few things in the universe that has a negative redshift, has a blue shift. Equals this, r max. How do I sort out r max? I sort out r max from here. Whereas v equals 0. I just get that. Right? So v equals 0 to r max, so I get r max from that. So I know everything here except the mass. So I just invert and I get the mass is 10 to the 12 solar masses, which is about 20 times luminance mass. 20. So we can see that there's a bunch of dark matter here. It's doing a bunch of work. It's accelerating Andromeda towards us. Okay, does anybody have any questions, other questions? I think we're good, I think. I don't think there's a reading due on Monday, is there? So nothing's due until I get some homeworks up. And that'll happen shortly. Have a good weekend.